All right, let's talk about something that gives a lot of physics students headaches: rotational motion. It's that chapter where everything literally starts to spin, and for a lot of us, it's where our understanding starts to get a little wobbly. But what if I told you it's not a whole new set of rules? What if it's just a new spin on the physics you already get?
Yeah, if this sounds familiar, trust me, you are not alone. You see this kind of post all over the internet. This topic just has a reputation for being the one that breaks people. The good news, though, that reputation is way overblown.
So what's the deal? Is it really the hardest chapter in physics? Well, in this explainer, we're going to tear that idea apart. The whole goal here is to give you a framework, a kind of decoder ring, that'll make this whole topic click into place.
But before we can really get into the spin of things, yeah, pun intended, we need to make sure we're totally solid on two really fundamental ideas. Seriously, getting these down makes everything else so much easier.
First up, this concept of a rigid body. Now, in the real world, everything bends, squishes, or deforms a little bit when you push on it. But for the sake of our sanity in physics, we imagine this perfect object that holds its shape no matter what. And this is so important because it means if one part of the object rotates, every other part rotates perfectly along with it.
Looking at a visual like this really helps it click. By pretending these objects are perfectly rigid, we can just ignore all the complicated stuff like bending and vibrations and focus only on the pure motion. It's a simplification that just cleans up the math beautifully.
And second, we've got the center of mass. The easiest way to think about this is as the object's perfect balance point. It's this one magical spot where we can pretend the entire mass of the object is located. If you throw a spinning hammer through the air, it looks chaotic, right? But its center of mass, that follows a nice, smooth, predictable curve. Okay, so with those two ideas in our back pocket, we can get to the core secret of this whole topic. And the secret is this: understanding rotation is all about seeing how it's just a mirror image of the motion you already know, moving in a straight line, what we call translational motion.
And here's the kicker: you actually do. You already understand the basics. If you get how a force makes a ball accelerate, then you have the exact mental toolkit you need to understand how a twist makes a wheel spin. You don't have to learn new physics, you just have to learn a few new vocabulary words for the same old rules.
And this table right here, this is basically the Rosetta Stone. For every single concept in straight-line motion, there is a direct twin in rotational motion. Instead of distance, we talk about angles. Instead of velocity, we talk about angular velocity. And now for the two big ones you really got to focus on. Force becomes something called torque, and mass becomes something called moment of inertia.
Let's really zero in on that last one, because let's be honest, moment of inertia is usually the concept that trips people up the most. What on earth is the spinning version of mass?
So here it is, plain and simple. Mass, or inertia, tells you how hard it is to get an object moving in a straight line. A bowling ball is harder to push than the tennis ball, right? Well, moment of inertia is the exact same idea, but for spinning. It's a measure of an object's resistance to being rotated. It's its rotational laziness, if you will.
But here's the tricky part, and why it's a little more complex than mass. An object's mass is just a number. That's it. But its moment of inertia? That depends not only on how much stuff there is, but, and this is critical, where that stuff is located relative to the point you're spinning it around. Think about an ice skater. Their mass is constant, right? But when they pull their arms in, they spin way faster. They haven't changed their mass, they've just changed its distribution, which lowers their moment of inertia.
Now, because where the mass is located matters so much, calculating the moment of inertia can get kind of hairy. Luckily, physicists came up with some really clever shortcuts. One is the theorem of perpendicular axes. All it says is that for flat, two-dimensional objects, if you know how hard it is to spin along two axes on the object, you can easily find out how hard it is to spin around an axis sticking out of it, like a frisbee. It's a neat little math trick.
And then there's this one, the theorem of parallel axis. This thing is a real game changer. It basically says if you do the hard work of figuring out the moment of inertia around an object's center of mass, you can then find the moment of inertia around any other axis that's parallel to it, just by knowing the mass and how far you moved the axis. Super, super useful.
All right, so we've got our new vocabulary. We know torque is the new force and moment of inertia is the new mass. So let's put it all together and see how things actually get spinning in the first place.
So what is torque? It's just the rotational version of force. That's it. A force is a push or a pull that makes something move. A torque is a twist that makes something turn. When you use a wrench on a bolt, you're not just pushing, you're applying a force at a distance to create a turning effect.
That turning effect is torque.
And this is where it all comes together so perfectly. You all know Newton's second law, F equals ma. It's probably the most famous equation in all of physics. Well, get ready for this. Just swap in our new rotational words. Replace force with torque. Replace mass with moment of inertia. Replace acceleration with angular acceleration. And what do you get? Torque equals I alpha. It is the exact same relationship. The underlying physics hasn't changed one bit.
And that right there, that's the whole takeaway. That's the secret. Once you really get this analogy, you see that rotational motion isn't some bizarre new corner of physics. It's the same fundamental principles of motion you already learned, just translated into the language of spinning. That so-called hardest chapter just becomes a new way to apply what you already know.
So this leaves us with a pretty cool final thought to chew on. We've spent all this time showing how spinning is just like moving in a straight line. But what if we have it backwards? When you look out at the universe, from planets and galaxies, all the way down to the quantum spin of particles, everything seems to be rotating. So which one is actually more fundamental? Is spinning the default state of the universe? And is moving in a perfectly straight line just a weird special case? Something to think about.